My dear student, colleagues, and all the viewers who are watching this program live from Facebook page Physics Center and School of Astrophysics and Astronomy and YouTube channel Kumar, I would like to welcome you all to our International Physics webinar. So good afternoon all here in Bangladesh and a very good morning to all those who are watching this program live from UK. So hope you are well and safe from Corona pandemic. So today it's our 175th International Physics webinar. So we are trying to adjust with this new normal situation. So we know that we cannot continue our normal academic program inside the campus due to the Corona pandemic. So we have to start our online program. I think you have already come to know that the Department of Physics, Pabna University of Science and Technology, has started its online program, including International Physics webinar, and we have successfully completed our 174th International Physics webinar, including two Nobel laureate speakers. And today it's our 175th. Today, I'd like to welcome you all to a joint session between the Department of Physics, Pabna University of Science and Technology, and the Department of Theoretical Physics, CERN, Geneva, Switzerland. And we have with us here today Dr. Azadeh Maleknejad, uh, CERN Theory Fellowship and Department of Theoretical Physics, CERN, and she has already connected with us. So I'd like to welcome our speaker. So, Madam, good afternoon and good morning to your part. So thanks for accepting our invitation, and it's my honor and privilege to host you in our International Physics webinar. So I think the viewers and the student, you have already come to know the title of the Students International Physics webinar. Title is The Spinning Field in Inflation and Their Remnants in the Sky. So madam, it's your time, you can start. And the student and the viewers, you can join with us by using this link, and you can also ask question by commenting.
Okay, let me. Can you see my slides?
Yeah, we can see your slide completely.
Okay, fine. Thanks a lot for the invitation, and it's great to be here with you, even though virtually.
Yeah, thanks.
So yeah, I'm here today to tell you about the very early universe and the spinning fields in inflation. Yeah, let us first start with a brief recap of what we already know about the physics of the very early universe. We know that our universe started too tiny, too hot, and probably from a big bang, and it's expanding ever since. For many years, it was filled with a hot plasma, and all the particles keep bumping into each other. But as it expands, it becomes colder and colder. To have a better understanding of what's going on, let us take a look in a neutral gas in room temperature. In summer, when the temperature is higher, the molecules have a higher kinetic energy, so they keep bumping into each other. However, in winter, when it's colder, molecules have lower kinetic energy and they're moving slowly, so they rarely actually interact. Now let's see what happens if we heat things up. Imagine that we have this gas made of neutral atoms, and then we keep injecting energy to it, so we make it hotter and hotter. At some point, it becomes hot enough so that the temperature and the kinetic energies are so high that all the electrons in the atoms can get free from their nuclei. And that's the moment that we have an ionized gas or a plasma. So now in the neutral atoms case, the photons can easily scatter, but in a hot plasma, photons have to interact with all these charged particles, and therefore it's opaque. In the very early universe, the opposite of this will happen. So at first, the temperature was so high, and we have this plasma, and the photons have to interact with all the charged particles, so it was opaque. But as the universe expands, it becomes colder and colder. At some point, it becomes cold enough so the neutral atoms formed in the early universe, and that's the moment that for the first time photons got free to stream in the plasma. And that's the moment that cosmic microwave background, or CMB, is formed. So CMB is the first snapshot of the very early universe. And in fact, if our eyes were sensible to microwave frequency, then the night sky wouldn't be dark anymore, because we could see a homogeneous and isotropic radiation all over the sky, and that's CMB. On the top of this perfectly isotropic radiation, there are teeny tiny fluctuations. And in fact, 1% of TV noise is because of CMB. Okay, and then the universe kept expanding and it becomes colder and colder. At some point, it got so cold that these initially hot neutral atoms got cold enough to gravitationally assemble and form the larger scale structures that we see today. Too simple yet profound. In fact, it turns out that our universe is too simple, too symmetric at very large scales. The leading paradigm to explain that unexpected symmetry in very large scales is the cosmic inflation. And that's a period of exponential expansion of space shortly after the Big Bang, during which the scale of the universe increases by a factor of e to 60 in a fraction of a second. Just to have a feeling about the size of that huge number, that's basically the same as if a bacterium suddenly starts exponentially expanding, and in a fraction of a second later, it becomes as big as a whole Milky Way. So it's huge. So what caused inflation? The exact particle physics of inflation is still unknown, but a scalar field slow rolling towards its true vacuum provides the simplest model for inflation. So the idea is that we assume that our universe was filled with a homogeneous scalar field beyond the standard model of particle physics that drives inflation. In order to have enough expansion, we need the potential to be almost flat during the time that we have experienced slow roll inflation. So far, so good. Yet things get way more fun once we turn on quantum fluctuations. We know that due to uncertainty principle, the quantum vacuum is not nothing or empty anymore. But it is this vast ocean made of virtual particles which are getting generated from vacuum, but then a fraction of a second later, they find each other and annihilate. So we end up with vacuum again. I mean, it's fun, but in the average, we have nothing. But in the presence of a background field, if this background field is strong enough, it can actually upgrade these virtual particles into actual pair of particles. And two examples of such background field that we are going to discuss in this talk are the electric field that can produce particles by Schwinger effect, and gravitational field that can produce particles gravitationally. In fact, the exponential expansion of the space during inflation can also produce particles. In the flat space, we start from vacuum, we have this virtual pair, but then shortly after they annihilate and we end up with vacuum. In an expanding universe, if the expansion rate is very large, we start from vacuum, we have a pair of virtual particles, but by the time they want to find each other to annihilate, the space underlying them expands so fastly that the poor particles cannot find each other anymore. And in this way, expansion of the space produce particles. The first person, this interesting phenomenon has been discovered by Edwin Schrödinger just at the beginning of World War II. But he was so shocked by his own discovery that he called it an alarming phenomenon. 80 years later, today, we think very differently about this, this effect. In fact, we think that cosmic inflation turns initial quantum vacuum fluctuation, stretch them, and turns them into actual cosmic perturbations. And so from primordial, this primordial cosmic perturbations, after cosmic evolution will turn and get imprinted on the surface of cosmic microwave background, or CMB, and eventually they form the large scale structures that we see today. And these fluctuations are so important and critical that if they were not around in inflation, they would have ended up with a perfectly isotropic CMB, and guess what? No large-scale structures. So in a way, we are the product of quantum fluctuations in the very early universe. So talking about this matter, this matter field in the universe. So this is made of mainly dark matter that we don't really know what is it made of, and only a small part of that is made of baryonic matter, which is what we made of. If we assume that from after inflation till today, everything was just based on the physics of the Standard Model, then it predicts almost equal amount of baryons and anti-baryons, which it means that this baryons and anti-baryons will eventually meet each other and annihilate. So we would end up with nothing. And the reason is that CP, which is this funny symmetry that can distinguish between matter and antimatter, is very mildly broken in the Standard Model. Observations, however, shows that our universe is highly matter-dominated, so it's mainly made of matter and not antimatter, baryons and not antibaryons. And so the baryon number over photon number is around 6 times 10 to minus 10, which, as you see, is much, much higher than the prediction of the Standard Model. So it means that there is some physics beyond the Standard Model that can break CP in sufficient way to produce this large imbalance between baryons and antibaryons. And that's one of the biggest mysteries that we are trying to answer. Okay, getting back to this primordial fluctuations, we already talked about the scalar part of this fluctuation at the time of inflation. This initial vacuum fluctuations has another part, which has the nature of gravitational waves. So these are spin 2 fields. And these primordial gravitational waves are basically teeny tiny waves in the fabric of the space-time that squeeze and stretch anything in their path as they pass by. And so if these vacuum gravitational waves, so we're talking about this Hij, which has 2 dynamical degrees of freedom, so I can decompose them into their 2 different polarization states. I decompose them in terms of left-handed and right-handed polarization states. And this is the equation of motion of this gravitational waves. Box H equals 0. So guess what? Both of this polarization states will have the same solution because they are just vacuum gravitational waves, and vacuum could not distinguish between these 2. And then they are also nearly Gaussian because they're just given by general relativity. And And it turns out that this this primordial gravitational waves are extremely powerful, and their power is in their weakness. The reason is as follows. CMB photons, as we discussed before, they can tell us about the early universe just up to the surface of CMB when cosmic microwave background is formed till today. However, these primordial gravitational waves, they are hardly to detect, yet they are extremely hard to block as well. So if they get detected, they can tell us about the physics of the early universe up to the surface of inflation, and that makes them extremely powerful and interesting. Okay, let us take a look at these primordial gravitational waves. If I expand these gravitational waves in terms of their momentum, what's happening is that during inflation, if I decompose them in terms of their physical momentum, let's imagine that we take a given k value, then A, which is the scale factor, is increasing exponentially during inflation, and the size of the cosmic horizon, which is specified what part of physics are inside the horizon and they are connected causally, is almost constant during inflation, but the scale factor increases. So during inflation, actually, the modes are getting stretched by inflation. So if this mode was initially inside the horizon, at some point during inflation, will get outside of the horizon. And that's when we call the point of horizon crossing. So why it matters? So this is a solution of this primordial gravitational waves, the vacuum solution. You see that deep inside the horizon, when these modes are just inside the cosmic horizon, they are basically like quantum fluctuations, and these are just like waves. But when they get outside of the horizon, eventually they take an almost constant value, and that's when they get super horizon scales. So they have an almost constant power spectrum, which is given in terms of the Hubble parameter during inflation. Yeah, I already told you that these primordial gravitational waves are extremely valuable for us, and that's the target of several CMB and other gravitational waves missions to look for this valuable signature in the sky. As yet, we know that observations are in perfect agreement with the concept of cosmic inflation. However, the exact particle physics of inflation is still unknown, and the standard models of inflation are based on one or some scalar fields. And the CP violation that we talked about that is required to explain the matter asymmetry is assumed to be related to neutrino sector. So in a way, we assume that physics of inflation is parity and CP symmetric. So it cannot distinguish between left and right and matter and antimatter. But wait a minute, what about gauge fields? We know that our universe is, we know that inflation happened at the highest energy scales observable to us. And we are surrounded with gauge fields. So they are the building blocks of the standard model and beyond. So what do they do in inflation? Can gauge fields contribute to physics of inflation? Do they leave an observable signature? How much they can change the course of cosmic history that we discussed before? In this talk, I will discuss that, yes, gauge field can in principle contribute to physics of inflation, in particular if the inflaton is an axion-like particle. And if they were around in physics of inflation, they leave a robust prediction for gravitational wave background, so they are testable. And in case that they were around, they lead to novel mechanisms to explain the matter asymmetry and dark matter production in the universe. So in principle, they can change a lot our understanding of the cosmic history. So how to have gauge fields that are active in physics of inflation? Normal gauge fields, which are given by Yang-Mills theory, they are acting like radiation. So during inflation, always these gauge fields are decaying like 1 over the scale factor. And during inflation, it means exponential decay, exponential annihilation, exponential dilution. So they will disappear. However, if this gauge field has some interactions that can keep pumping energy to them, they can survive the cosmic inflation. And one famous example of such interaction is an axion-like particle, which is naturally coupled to gauge fields. So if the inflaton, for example, is an axion-like particle, it can naturally generate gauge fields during inflation. But then it leads to the last challenge of having gauge fields in cosmology, and that's about the spatial isotropy and homogeneity that we see in the large scales in the universe. And in case that I have a normal U1 gauge field with a background solution, it immediately breaks the spatial isotropy. So it cannot be the case. However, it turns out that if instead of a U1 gauge field, I have an SU2 gauge field, which is this kind of vector field that has 3 different colors with this internal SU2 symmetry between its different colors, then it's possible for this gauge field to have a spatially isotropic solution. And the key is this the isomorphy between SO3, the group of rotations, and SU2, which is the internal symmetry of these gauge fields. And let's have a closer look at how it works. Let us choose the temporal gauge. So we said A0 equals 0. And let us turn on background solution for any vector fields. After performing a spatial rotation, then they will all rotate like vectors. So it looks that they are breaking the spatial isotropy. In fact, in case of the U1, they are actually breaking the spatial symmetry, spatial isotropy symmetry. However, in the SU2 case, although I fixed the gauge to temporal gauge, there are still residual gauge transformations, which has the same structure as the rotations, thanks to this isomorphy between the 2 algebras. So for any rotation that I choose, I can find the right gauge transformation to cancel that, and I end up with a perfectly isotropic and homogeneous physical solution. And this is not just for SU2. It can be for any SUN once we live in its SU2 subsector. So it's for any non-abelian gauge field, you can find the solutions. And then you may ask, okay, so there exists this spatially isotropic background solution for the gauge field. But what if I start from somewhere away from this perfectly isotropic solution? What would happen? Would I end up with a with an anisotropic background, which is inconsistent with the observations, or these anisotropies will get diluted and I would end up with a perfectly isotropic solution? It turns out that in this mechanism, the isotropic solution is the attractor, and these anisotropies will get diluted by inflation. And the reason is because the axion, which actually sources the gauge fields to survive inflation, only sources its isotropic part, not the anisotropic part. So the anisotropic part acts like a normal radiation and disappeared. Okay, enough words. Let me show you some actions. The story of non-abelian gauge fields in inflation started with a gauge inflation model, which happened to be my PhD thesis. And this is basically Einstein gravity plus a normal gauge theory, which is the Yang-Mills, and some self-interactions between the gauge fields in the form of FF tilde squared. And why this? Because FF tilde squared, if you write the energy momentum tensor coming from the stem, you will realize that it has the same structure as a vacuum, as a potential for a scalar field. So in case that this dominates over the Yang-Mills term, we will have the similar scenario as the scalar case, because we will have a slow roll inflation that will eventually end in radiation era, because this term will inject energy to the Yang-Mills term, which acts like radiation. And gaugeflation is an effective field theory coming out of a larger model, Kumar, which has been worked out 1 year later, and that's basically Einstein gravity plus a scalar an axion inflation with the cosine potential, and some gauge fields which are coupled to this axion field with this Chern-Simons interaction. And then inspired by these two models, several different models with SU2 fields in inflation have been proposed and studied in the literature. And here is an incomplete list of different realizations. At some point, I just stopped counting, but the last model appeared last week. So the original models are ruled out by the data, but the other model that I showed you are inconsistent with the data. And the simplest realization is this minimal scenario of SU2 axion inflation, in which I replace the cosine potential with the potential which is flat enough by itself. So let me just briefly tell you why these two simple models are ruled out. So the cosine potential, which is used in Kumar model, is not like a really flat potential. So if it wasn't because of the gauge field, we couldn't have slow roll inflation and enough E-folds. But although the potential is actually steep, but the interaction with the gauge field, if this coupling lambda is large, then provide a strong friction. So now the axion, which is moving in its potential, faces this very like a strong friction, which is slowed down its dynamic and injects energy to the gauge field. And that's how it makes slower inflation possible. However, this huge lambda value, which is required here, is actually not in agreement with the data, and also theoretically comes with some issues. However, if I, instead of a cosine potential, I assume that it's a flat potential by itself, then I don't, I can actually relax the value of lambda, and then I get in agreement with the data and theory. Okay, so as a result, we realized that SU2 or any non-abelian gauge fields can contribute to physics of inflation and respect the spatial isotropy, and as a result, a new class of inflation models with SU2 gauge fields and axions has been introduced that we call SU2 axion models, and it opens a new window to particle cosmology because it leads to new observable signatures in the sky, which are chiral, non-Gaussian gravitational waves that we are going to discuss soon. Here, in general SU2 axion models, both the gauge field and the axion have background values, and they break parity and CP. So in these models, inflation can distinguish between left and right in matter and antimatter. And so this is the vacuum structure of SU2 axion inflation. In the vertical axis, we have the axion field, and the horizontal one, we have the gauge field background. In case that the axion field in inflation has a positive value, we live in the red slow roll trajectory. However, if the vacuum solution of the axion is negative, we live in the blue slow roll trajectory, which is the parity conjugated version of the red solution. Particles, the scalar fields, which doesn't have spin, and the background cosmology are not sensitive to this non-trivial structure vacuum. However, particles with spin, like fermions and spin 2 fields, are sensitive to this, and that leads to interesting particle production that we are going to discuss here. Okay, so now we have a gauge field and therefore an electric field during inflation, and that can also produce particles. So in a vacuum flat space with no electric field, we start from vacuum, we have this pair of virtual particles, and then they get annihilated and we end up with vacuum. In case that we have a very strong electric field, and you see this number is huge, then we start from vacuum, we have this pair of virtual charged particles, but then because this electric field is very strong, it can actually upgrade and break this loop and makes them actual particles. And that's this effect has been discovered by Schwinger, and this is a highly non-perturbative quantum effect. As you notice, this electric field, which is required for the Schwinger effect, is huge, and therefore in flat space this effect has never been observed. However, in the very early universe, when the energy scales are huge as well, and in this specific setup we have a gauge field in inflation, this effect can actually be can actually happen and also leave some observable signatures. Here we have the map of what's going on. First, we have this cosmic inflation made of axions and SU2 gauge field, which are coupled to them. Parity and CP are violated in physics of inflation. And then because we have this gauge field, it can produce all the particles which are coupled to it, like a scalar field, like a Higgs, like dark fermions, which are coupled to this gauge field, and gravitational waves or any spin 2 fields which are coupled to it that we are going to discuss. And then finally, these particles which are generated in inflation can lead to observable effects, like this new spin 2, which is coupled to gravitational waves and produce interesting observable effects on primordial gravitational wave background. And also this dark fermions, which can get generated in inflation, they can also produce new mechanisms to explain the matter asymmetry and the dark matter that we observe today. So let us first take a closer look at this new spin 2 field that we discussed. Once I perturb the gauge field, this SU2 gauge field around that spatially isotropic and homogeneous solution, there is a new tensorial mode in the heart of that gauge field, which I call Bij. This Bij has the same structure as the primordial gravitational waves, so they are naturally coupled to each other. Once we actually solved the field equation of this Bij, we realized that it's chiral. So if I decompose it into its two different polarization states, left-handed and right-handed, they will get generated differently. So they are chiral. And then this new tensorial mode is linearly coupled to gravitational wave, and therefore they get sourced by this gauge field. And as a result, our final gravitational wave solution are made of two parts. The first part that I showed in blue, these are the vacuum solutions that we discussed before. They were unpolarized and nearly Gaussian. And this red part, which are actually sourced by the gauge field, and they are basically a carbon copy of their source. So similar to B field, they are chiral. And since these gauge fields are self-interactive, they are non-Gaussian as well. And that leads to novel observable signatures on CMB, which is going to be probed by future CMB missions like LIGHTBIRD and CMB-S4. Okay, then also CP, which is the symmetry that can distinguish between matter and antimatter, is also broken in this inflationary solutions. Therefore, this class of models are a natural setting to explain the matter asymmetry. And finally, scalar fields and dark fermions, which are coupled to this gauge field, they can also get generated in inflation by the gauge field, and also by chiral anomaly in inflation, which is this guy here. And this fermions can explain the matter asymmetry that we observed today, and also make part or all of the dark matter. So the standard model of particle physics, which is the most rigorous theory of physics in the whole history of physics, unfortunately, when it meets with cosmology and astrophysics, it gets ridiculously incomplete. And the current big questions of modern cosmology and particle physics are the particle physics of inflation, the origin of the matter asymmetry, the particle nature of dark matter, and primordial gravitational waves as the only missing prediction of inflation. And then from the particle physics point of view, fundamental discrete symmetries and their violation played a key role in understanding of the standard model and beyond, like charge symmetry, C, and parity, P, violation in weak interactions, like to formulate the weak interactions, and the CP violation to explain the matter asymmetry. Yet in most of the inflationary models, like the standard scenarios, it is assumed that parity and CP are the symmetries of inflation. In this SU2 axion inflation model that we discussed here, both parity and CP are broken, and therefore they can relate. They can explain and relate all of these seemingly unrelated phenomena in early and late cosmology. And if you think about it, inflation is the only place that CP can actually be broken spontaneously without the danger of the domain wall problem. Okay, we already talked about the tensor perturbations in inflation. Now let's get to the scalar, like dark Higgs production and fermions. Let me No, let me just briefly tell you more details about the tensorial perturbations. Here we have the perturbed gauge field, and we have this Bij, which is this new tensorial mode. We discussed about this vacuum structure of the model, that we have two kind of slower trajectories, red and blue. In red trajectories, delta C parameter here is positive, and in the blue trajectories, delta C is negative. And so here in this equation, I decompose, I write the field equation for these two different polarization states of the tensorial mode of the gauge field, and you see the effective frequency squared is polarization dependent. And in case the delta C is positive or negative, one of these modes will get a short phase of tachyonic instability, meaning light of particle production, while the other one is just a normal mode. Let us assume that this delta C is positive, so we live in the red trajectory. Then from here, you see that the plus helicity, plus polarization state can have a negative frequency squared for a short period of time. And that means that it can lead to particle productions. In this white box in the right, we have these two different polarization states, B plus and B minus. And you see deep inside the horizon, they are roughly the same. But as we approach the point of horizon crossing, K over AH equal 1, you see that they have very different behaviors, because the dashed black one, which is the one that doesn't experience this short phase of tachyonic instability, is just decaying. But the red one, which experienced this short phase during which its effective frequency squared is negative, will receive a large enhancement at the point of horizon crossing. But then after horizon crossing, they all decay. So now our horizon is covered with lots of this B particles, but just the B plus polarization. So it's just it's a kind of a chiral field. And so why it matters, as we discussed before, the gravitational waves are now linearly coupled to this extra tensorial mode. And this is the field equation of gravitational waves. The blue part, when the right-hand side is 0, is just a vacuum gravitational wave. But the right-hand side is the source coming from the gauge field. So now gravitational waves have two uncolorated terms. The blue part, which is just the vacuum solution, these are unpolarized and merely Gaussian. And the pink part, which is sourced by the gauge field. So therefore, they are polarized because their source is polarized and also non-Gaussian. And that's super interesting, because now it leads to a novel observable signature on CMB, which is the equilateral shape of tensor non-Gaussianity, which is going to be probed by Lightbird and CMBS4. But it's not all the story, because it's even more fun. In case that in most of those scenarios, gravitational waves are blue tilted. And so here we have the omega gravitational waves in terms of frequency. As you see, even if, so let's look at this blue line here, you see that even at the scale of CMB, if it's the signature is small, because it increases with frequency, eventually it can be large enough to be even probed by future laser interferometers. And things are even way more fun, because now in the nano hertz frequency, we have new possible experiments, astrophysical experiments as well. So the future is very bright. Let me skip this slide, but just briefly tell you that because parity is broken in this SU2 axion inflation models, unlike the standard scenarios of inflation, we have parity odd CMB correlations, which are otherwise would be missing. Okay, let's just briefly talk about the scalar and fermion production. So now the scalar fields on the top of the inflationary background can get generated by this gauge field if they are charged by under this gauge field. But something funny is actually happened. If you actually solve the same scenario, but with a U1 gauge field, let's assume that we have a normal electric field, which is a U1 field. And so you break the special isotropy, you turn on a U1 gauge field, and then solve the scalar particle production when this scalar field is coupled to this U1 gauge field. Then you will see by increasing this background electric field, you will produce more and more of these scalar fields. In the SU2 case, that is the interest of this talk, and that's what we are discussing here, something different happened. And in fact, we realized that, so now we have this isotropic SU2 field configuration in the background, and it has both electric field and magnetic field. When we solve this the system, we realized that by increasing the background value of this gauge field, which is actually increasing the electric field, it decreases the amount of scalar particle production. And at first it was puzzling because it was a surprise based on our experience of the anisotropy U1 case. However, the physical reason for this behavior is that this isotropic SU2 gauge field have electric field and magnetic field, and by increasing the electric field, we are actually increasing the magnetic field because it's the isotropic solution. And the magnetic field is actually somehow contribute to mass of these particles effectively. So by increasing the electric field, we are making it more costly for the electric field to produce these particles because their effective mass will get increases by the magnetic field. So it was super fun to realize that this in the SU2 case, the scalar production is not efficient. Now get to the fermion part, the spin 1/2 fields. We can have fermions which are coupled to this background gauge field, and also they can, in case that they are massive, they can also get generated by the axion as well, but if they are massless, they cannot. Because in the SU2 axion inflation, parity and CP are broken, it can produce a net fermions in inflation, and therefore it leads to a new non-thermal mechanism for generation of massive or massless fermions in inflation. And just if I want to briefly compare the efficiency of these different particle productions, here the blue arrow shows the scalar production, which I told you is not efficient that much. Then the larger contribution, which I showed in pink, is for fermion production, and finally the largest is for this spin 2 or the new tensorial mode in the gauge field. And so as you see, somehow the efficiency of this particle production increases by their speed. Okay, now let me, it gets me to the summary and the outlook. SU2 axion models of inflation have a very rich phenomenology and enriches the particle cosmology. Both parity and CP are violated in this class of inflationary models. There is a new tensorial mode in the gauge field, which sources primordial gravitational waves and provides a smoking gun for this primordial SU2 gauge field in the sky. This source gravitational waves are chiral and non-Gaussian. And then the fermions, which are coupled to this primordial gauge field, they can also get generated in inflation. And I didn't have time to discuss it in this talk, but interestingly, if you embed this idea in left-right symmetric model of particle physics, you will realize that this mechanism leads to a common origin for inflation, dark matter, and matter asymmetry in the universe. And so it leads to novel mechanisms for baryogenesis and dark genesis, and naturally explain the cosmological coincidences. Thank you very much.
Yeah, thank you for your wonderful presentation. So we have got few questions. So if you allow, we can start our discussion session. So the first question. So when did the CMB form in the universe?
When you mean, let me get to that slide. Okay, so you see, we started with a very hot universe when we have this ionized plasma. So it was opaque for the photons. The CMB is the moment that this photon for the first time got free to stream in the universe. So it happens when the temperature gets lower than 1 electron volt.
Okay, so thank you. We have another question. So why antimatter have disappeared from the universe?
Sorry?
So why antimatter have disappeared from the universe?
I didn't understand why antimatter.
So the question is that why antimatter have disappeared from the universe? So,
Excellent question. Yes. Well, let me. Okay. Slides here, right? Oops. Sorry, I'm just looking for the right slide here. Oops, sorry. Why it's so slow in? Okay. So, excellent question. So if it was just the standard model, it predicts almost equal amount of baryons and antibaryons. And if you compute the baryon number over the number of photons in the universe, they are almost equal to the number of antibaryons over photons. And this number is around 10 to minus 20. However, the observations shows us something different. And in fact, the reason that we are here today to even talk about it is because that, thanks God, nature was kind enough to break the CP. So the idea is that there is some mechanism shortly before BBN, Big Bang nucleosynthesis, that the CP is effectively broken by some physics that we don't really know exactly. We have some rough ideas about its nature. And if this happens, that we assume that somehow it produces lots of baryons, but the antibaryons, so imagine that this antibaryons over N gamma is just the one that predicts by the standard model, but this N baryons over N gamma is this much larger number. So yeah, if that happens, then this antimatter part will get annihilated with a very small part of the matter, and the rest will be just matter. Did I answer your question?
Yes. So we have another question. So what will happen when axion interact with the standard model particle?
Excellent question. So it depends on what axion we're talking about. In this talk, so the most famous axion is this QCD axion, which is a light field, and it's naturally coupled to the QCD to gluons, which are the carriers of the strong forces. Okay. Oops. Why is just okay? Maybe this one. You see, an axion, regardless of what kind of axion we're talking about, they can naturally couple to gauge field with this kind of interaction, which is phi, the axion, times FF tilde. So FF tilde, if the Yang-Mills theory, F squared is electric field squared plus magnetic field squared. But this FF tilde is electric field times magnetic field. So it's different than F squared. And this is how they are coupled to gauge field. But then depends on what kind of axion we're talking about, this gauge field would be different and would have a different potential and different masses. In this specific scenario, I assume that this axion is not the QCD axion, but this axion which is very heavy. So its potential is large enough to provide enough energy density for inflation to happen.
Thank you. This may be the last question. So, ma'am, what is the CP violation?
Okay, excellent. What is the CP violation? So CP is this, so you know about these three fundamental discrete symmetries of nature, C, which is the charge conjugation, and so the C is a discrete symmetry that transforms a field with a charge, let's say Q, and turn it to its charge conjugated version with a charge minus Q. Then the other famous discrete symmetry is parity, which turns a left-handed or right-handed particle and turns it to its other-handedness. So if it's right-handed, it will take it to left-handed. If it's moving in this direction under parity, the parity conjugated of this particle will be a particle which is moving in this other direction. And the last one is time translation that actually switches the direction of time. And then we have some composite discrete symmetries like CP, and CP is actually taking a particle with charge Q and move in this direction and take it to a particle which charge minus Q, which is going to the other direction. And if these particles are actually meeting each other, they annihilate each other. So they are each other's antiparticle. And that's a very important discrete symmetry, that there is a physics beyond the standard model that's responsible for the CP violation. And because this fundamental symmetry is broken, at some point universe could actually create more baryons than anti-baryons, and eventually there are some leftovers from that initial baryon anti-baryon distribution, and our universe is our matter, our baryonic matter is possible today. Did I answer your question?
Maybe. So thanks for your wonderful presentation and discussion session. So I would like to thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation. So the main aim of our program is to motivate, and I think by your lecture, our student and viewers are motivated. So and they may understood about the inflation and their remnant in the sky. So thanks again, and hopefully in near future we'll arrange another webinar with you. And after the COVID, I'll definitely invite you for our beautiful country, Bangladesh, for a face-to-face session. Thanks.
Thanks
Have
a
a
lot
nice
for
day.
having me. It was great to join you today. And yeah, just send me an email if you're interested, or if you like to know more about some
Yeah,
of
of
these
course.
ideas.
Yeah, of course. Bye. Have a
Bye.
nice day.
You too.
Bye.
Bye.